Good morning, ENET 140 Op Amps class. This is Bellingham Technical College's ENET 140. We're in winter 2020 quarter, and this is our second of 3 recordings on Fiore's Op Amps textbook, Chapter 3, which deals with all of the benefits and cautions for use of negative feedback. At the end of our last recorded lecture, we derived this equation for closed loop op amp gain expressed as a voltage ratio for a series parallel, that is series on the input and parallel on the output configuration of negative feedback. And just to go over that again, we have the open loop gain in the numerator of this fraction, and then we have the sum of beta, which is the feedback fraction for the circuit, times the open loop gain plus 1 in the denominator. And when the open loop gain is large, which it almost always is, this approximates down to just simply 1 over beta. So closed loop gain in the series parallel configuration is approximately 1 over the feedback fraction. Now we're going to dive into the effect that configuration of negative feedback has on bandwidth. So we're going to apply this ASP, or closed loop gain ratio, equals AOL over beta AOL plus 1 to the frequency dependent portions of the Bode plot. Up till now we've been working, whether we said it or not, in this midband region, and we'll zoom in a little bit here on our friend, the gain versus frequency plot for this is open loop gain versus frequency plot for a typical op amp. And if you remember from our studies in Fiore Chapter 1, if you have a capacitor on the front end of your op amp circuit, which would be called a leading configuration, your gain will increase at a rate of 20 decibels per decade of frequency increase up to the onset of the midband region. That onset is marked by what's called a critical frequency, at which we have half the gain power equivalent that we do in the midband, and that's your F1 or F critical 1. You move through the midband, and in here you've got a flat line, so your gain is the same regardless of frequency. This is the midband. This is where we want to work. Gain is frequency independent. Since all op amp circuits have a certain amount of lagging capacitance or capacitance on the output, we encounter that same kind of 20 decibel, in this case loss, with an increase of frequency in our lagging region here at the high frequency. So all op amp circuits will end up experiencing this gain loss as you go to higher and higher frequencies. Some can be designed so they don't experience this leading region, but they all have the lagging region. So no op amp circuit will operate with frequency independent constant gain at a sufficiently high frequency. But since chances are we're going to want to operate at high frequency sooner or later, we want this F2, this half power equivalent frequency that marks the high end, the high frequency end of the midband region. We want that as high as possible. That way we have the greatest frequency operating region for our op amp. So up till now, we've just simply measured it. We've maybe calculated our F1 and F2, especially our F2, based on some knowledge of the capacitance and real resistance of the circuit, using what we know about impedance and our AC active and resistive component addition. But we haven't looked at the effective feedback. We've only looked at those calculations from the standpoint of, an op amp operating all by itself. So now we're going to start with a little bit of a comparison to get an idea of the power of negative feedback when we want to operate in this region. And you can tell, I'll give you a hint from this graph. The solid line here represents our 20 decibel per frequency decade loss as we go out in that lagging region beyond the midband and increase our frequency. This little dotted line labeled ASP is a little bit of a schematic representation of what our series parallel negative feedback should be doing to the gain, and that should be a prime, because all of these gains on this particular plot, of course, are decibel. And we will go back and forth between decibel and gain ratio as needed. Just a word on that: if you are using this equation that we derived last time for closed looped gain, be warned that these should be voltage ratios, not the log of voltage ratios. So as we derived it in terms of a V in and V out ratio, very specifically. Okay, so back to our frequency plot, where we will, unless otherwise specified, be using voltage ratios again. So say we have an op-amp circuit with an open loop, upper critical, that's half power, frequency of 100 Hertz. So F2 right here is 100 Hertz. And the open loop gain at that point is 10,000, which is equivalent to 80 decibels. So that's this point right here. And that's the last time you're going to see that high of a gain as you move higher in frequency for this op-amp, because you know it's going to start taking that 20 decibel per decade drop. And you are using a feedback network where 10% of the output signal is fed back. So that's equivalent to a beta of 0.1. Okay, if we were going to calculate the open loop frequency, the open loop gain at a frequency of 10 times our upper critical. So that would be at 1,000 Hertz. So we want the open loop gain right here. You can see it's way lower than it was right here. In fact, it should be 20 decibels lower. And it is. It's 60 decibels, or an open loop gain of 1,000. So we dropped from 10,000 to 1,000 as we went from this frequency to this frequency. Oh my goodness. If you had a signal coming in at this higher frequency, and you were expecting to get a certain gain, and you only got 1/10 of that gain, you might not be able to read it or process it. And if you weren't expecting that, you'd be stuck. You couldn't get the data from your instrument or whatever you're using this amplifier for, so that would be bad. But if you were using negative feedback with a beta of 0.1, what would the gain be up here right at the edge of the midband? Well, we can plug into our formula that we just derived, and we'll assume, of course, that we have a series parallel configuration of negative feedback, so we can use this formula that we just derived. So in the case where we're rolling off the edge of the midband here, we're going to plug in our open loop gain in the numerator, and then we're going to multiply, we're going to plug it into the denominator, multiply by our beta, and get 1,000, because 10,000 times 0.1 is 1,000. We add 1 to it, and we have about just shy of 10, 9.99. Now, chances are, whatever our signal is will maybe not be quite at the supply voltage with a gain with our closed loop gain of 9.99, but we should get a gain of 10. Should be plenty to serve our needs. But oh well, what if we drop our open loop gain as we roll off into our higher frequency region where open loop is smaller? So what we don't want is to go, oh my gosh, we only started with a closed loop gain of 10. Now that we dropped the open loop gain, we're going to have enough gain. Well, let's see. Let's plug into our formula again. So we're going to operate now at 1,000 Hertz. And so our open loop gain has been reduced from 10,000 to 1,000. So we have 1,000 in the numerator, and we have 1,000 times our beta, which is 0.1 in the denominator. So our closed loop gain at the higher frequency, ASP at 1,000 Hertz, is 1,000 over 101, which is about 9.90. Wow. No significant loss. Oh my goodness. Rather than losing an order of magnitude gain by going up a decade in frequency beyond the midband range, we lost like 1%. Probably not even significant. So, and there's that in words. So for a decade of frequency past the upper critical, that's F2, the open loop gain drops by 10 times. Closed loop gain drops by 1%. There is the power of closed loop gain in increasing bandwidth. So we can go happily along amplifying at pretty close to the mid-band levels for much, much higher frequencies on that upper end. The same would hold true for the lower end if we didn't have a circuit that was designed to work in DC and we were rolling off. We would extend that range as well. And in fact, and here's a caution just to remind you, this is just a step back in the past here, back to chapter 1, just as a reminder, this is what our leading network looks like on this end. And just to remember that when we're working with our lagging network, which is, here's our circuit, the representation of our op amp that gives us that open loop roll-off behavior, just as a reminder that because we have that capacitive element at the end, just remember you will have, that imaginary expression associated with your open loop gain. But for practical purposes, you can just plug into this formula. Okay, maybe you would like to know what your bandwidth change is for any given feedback network. Say you have your open loop gain, you know what you are contemplating working out in that range where you're having that 20 decibel per decade of frequency loss, and you're adjusting your beta, and you want to predict ahead of time, will you still be in the midband? Or are you going to get to the point where even with your negative feedback, you might lose some bandwidth? Well, we can go back to our formula, our original formula for our critical frequency and the gain at that frequency, and then substitute in our closed loop parameters. And we don't have the derivation for that here, so we just have the formula that you can use, but you could derive it if you wanted. So I'll just read it to you. The upper critical frequency, so that's that F2 right here, in the closed loop condition is equal to that same critical frequency in the open loop condition times the loop gain. Oh, the loop gain, the sacrifice factor. There it is again. And that's actually this expression in the SP feedback configuration. So the same term that we saw back here in the denominator relating open loop gain to closed loop gain when gain is expressed as a voltage ratio, if we're looking at that same effect on bandwidth, and so how far out to what higher frequency we're going to move our half power upper critical, we get the same expression. You will see this sacrifice factor or loop gain factor repeated again and again in the derivations and formulas for the effects of any particular negative feedback loop on the closed loop properties versus the open loop properties of the circuit. So you'll see that you will either multiply or divide by the loop gain, or otherwise known as sacrifice factor, to relate most of those. So a similar change would occur for a lead network, except we would be lowering the critical frequency. So we will widen the area in which we have a frequency independent gain when we go to a closed loop, and we will widen it by the sacrifice or loop gain factor. So let's apply that to a hypothetical real circuit. So here's our kind of prototypical series parallel negative feedback op amp, and we know it's series parallel because we have our signal coming in and it doesn't branch. It's in series with the op amp, no parallel branches, but our output signal has a branch. It has a parallel configuration. It can either go through the feedback network or out to the load. So series parallel. So we know we can use the formulas we just derived. So say this thing has an abysmal open loop gain for an op amp of only 200. I mean, that's like what we'd see for a regular just BJT, but oh well, it's what we have. And suppose that we have our upper critical frequency, so the end of the midband, the upper end of the midband range is at 10,000, or excuse me, yes, 10 kilohertz or 10,000 hertz. So, you know, that's pretty high frequency, so maybe the op amp designers decided to trade midband gain for a higher working range. We're going to feedback 4% of it. We're going to see if we can make this working range even bigger, and we're going to see how much of that that open loop gain we lose in the process. So what do? Well, let's start by getting our our closed loop gain. How do we do that? We apply the formula we just derived. So we take our open loop gain, which we got off the spec sheet, and we divide it by 1 plus the open loop gain times the amount of feedback we're deciding to use, our feedback fraction. So we have 200 divided by 1 plus 200 times 0.04, and we get 22.25. So we drop by a little under an order of magnitude on our open loop gain. So let's see what kind of gains we make, pun intended, in our upper critical frequency. So we're going to use the formula that we just looked at here. We're going to say that our upper critical closed loop is equal to our upper critical open loop times that loop gain. So what happens when we plug that in? So we start with the original open loop upper critical frequency of 10 kilohertz, which we got from the spec sheet, and we multiply by 1 plus 200 times 0.04, and this turns out to be 9. So we go up by just shy of an order of magnitude, and so now our F sub 2, or our upper critical frequency, instead of being 10 kilohertz, is 90. And if you'll notice, it's not because we're effectively dividing and multiplying by the same number. Our loss in gain in the midband, our closed loop versus open loop gain, and our extension of the midband region are in proportion. So you could say that the product of your gain and your upper critical frequency is conserved. So what you lose in one, you gain in the other. So if you're thinking of that as an area under the curve, the area is conserved. So again, this is the idea of sacrifice factor. This is why this particular factor that's used to show the effect of feedback on our op-amp circuit properties is called the sacrifice factor, because you sacrifice some gain and you get proportional improvements in other things that might be far more important. So we sacrifice some gain in the midband, and then we extended the midband significantly. So now we can amplify a frequency at 80 kilohertz and get the same gain that we would for a frequency at like 5. Okay. All right, so now that we're all sold on the great benefits of negative feedback, stabilizing, and all these good things, how do we make one? Well, we can make one really easily. All they have to do is diminish the signal that we're taking from our output, like here at point B, and feed it back in, pun intended, to the inverting terminal of the op-amp. Theoretically, we could feed it back into the non-inverting terminal, but we would have to have some kind of circuit which flipped the phase around 180 degrees. Since the op-amp circuitry itself has a means to do that in the form of the inverting terminal, it makes a lot of sense to just take something that will select a portion of our output signal, like a voltage divider here, and just connect it right into the inverting terminal. So this is one of the simplest, and this is sort of the I'd call it like the classic series parallel negative feedback configuration where you have a feedback resistor and what's called an inverting input resistor, R sub F and R sub I. And they have those subscripts for a reason, because if you look at the voltage drop over R sub I coming up from ground, so whatever current flows through this resistor will raise the voltage at this point by that much, by the voltage drop, and that is the voltage at your inverting terminal, because there's just a wire here, there's nothing else. And by the same token, you can calculate the feedback voltage, or the difference in the output versus this point, by the voltage drop over RF. So RF and RI both combine as a voltage divider to change the voltage from this point to this point, but RF is the one that is basically selecting how much of V out comes back in and is fed back in. So a little bit different function, that's why it's called the feedback resistor. If we want to get really strict, excuse me, we can use the same methods that we used when we were doing our KVLs and measuring input and output voltages in our BJT circuits, and apply it here with a few rules about what has a high and low input impedance in our op amp, and look at the resistance to ground from point B. Excuse me. Yeah, point B, which is odd because that's the output, but we're going to use that to calculate the input impedance nonetheless. So we'll just take a look at it. And again, we're following right from Fiore's book, so you can use that as a reference in case there is an error. And if I encounter an error, of course, in any of these lectures, I will point it out immediately or re-record, so don't worry. So we look at the resistance to ground from point B. Well, you can go back through the op amp and through our input signal, or you can go straight to ground. You kind of have two choices. So point B is in parallel with the input to the op amp and with a series combination of those two resistors. And again, the resistance from the inverting input terminal to ground is just Ri in parallel with, assuming these are connected within the op amp, because they are at some point, the input resistance. So we're just using this point and the inverting terminal as a bit of a construct, and we're assuming that we can go through the op amp somewhere via Zin and get some kind of impedance from this point to this point, or from this point to this point. So Mr. Fiore just states that, and so he's obviously using some kind of circuit model to do that. It does not show it explicitly. We can, having just stated that, we can relate these two expressions to our beta, which ends up simply being the ratio of this one to the upper one. And if you think about that, that makes a little bit of sense, because the feedback fraction is going to end up being the voltage, the feedback voltage, which is going to end up at the inverting terminal, divided by V out. So it's the fraction of V out. There's the voltage at the inverting terminal, and if the impedance to ground is defined by the impedance from point B to ground, if you multiplied this by a current Zn in parallel with that series combination, you would get the potential to ground. So we do another approximation here, which we will rely heavily on in Chapter 4 when we start doing some practical circuit design with op amps. Let's assume that Zn is huge, which it very often is for op amps. likely because you've got that differential amplifier up front with current sources that have huge input impedances in them, which is something we relied upon when we were doing Z in and Z out in those simpler circuits. So let's assume that Z in is huge. If it's huge, nothing's going to go through that branch of the circuit, and so the Z in will just disappear from this expression, and you'll end up getting an expression for beta that says it's just Rn divided by Rf plus Rn, which is the same way of saying no current is flowing through the op amp. No significant amount of current is flowing directly from the input signal to the output signal. So we have a very high Z in. So that means the difference in voltage points here and here is solely a product of the feedback resistors. So we're going to assume that's an open going in and going in. So a signal is sensed, and then all the current that flows through the output is coming from those supply rails. That's another way of saying that. So we just have a voltage divider. Our beta is now simply the voltage ratio created by these two resistors. And we did a little bit of a seat of the pants derivation to show that, showing the role of Z input, which we were trying to derive, or will try to derive later, and then those resistors. So a bit of a roundabout way of saying it, but beta, assuming infinite input impedance, is just the voltage divider ratio. So now we have a beta, very simple beta for negative feedback. So if we want to put that into our closed loop gain expression, we can put it in right there. If we say that this is approximately 1 over beta, we can say that the closed loop gain is the inverse of this. So we flip it over and we can do some simplification. We could say that the closed loop gain in this series parallel negative feedback configuration is Rf over Ri plus 1. Note that practical ranges for these resistors should be in the 10K to 100K range. That's something you'll see in our textbook. So that's what's the recommended range based on most practical op amp characteristics. So we can do a quick example of that, and we'll maybe take a break. So we have an acoustic input signal requiring 20 decibels of gain. And we have our feedback circuit in our op amp. Okay, so we need a V out over V in. Take the log base 10 of it, multiply by 20, and we need to get 20 as a result of that calculation. So if we express 20 as 20 decibels as a voltage ratio, we end up with 50,000. So that's our, oh, excuse me. Nope. Apologies. We don't. We were given 50,000 as the open loop gain of the op amp. Need a little bit more coffee this morning. And we were given 60,000, or excuse me, 600 ohms as our input impedance. So 600 kilo ohms. We need a 20 decibel gain as our closed loop, our ASP. So the question asks us, or hypothetically our colleague is asking us, hey, plug in a couple of feedback resistors that will give me this gain for this op amp that I selected. Oh, and tell me what the new input impedance is with your resistor network. So we can go ahead and do that. So all we need is a beta, and we can calculate our closed loop gain and then see if it gives us our 20 decibels. But we might have to work that backwards because we need a beta which will give us that. So we'll just read from what we have here. We're going to express our open loop and our closed loop gain in the same units. Use ratios, not decibels, because this equation was derived with respect to voltage ratios, as we said earlier. So we do that over here. do a little algebra. We multiply this denominator by our ASP, and we're left with open loop in two sides of the equation. We're going to distribute our ASP, collect terms that have a open loop in them, separate them from closed loop, divide, and get beta isolated. Okay, so we take our desired output gain of 20 decibels, convert it to a voltage ratio, and we find that a voltage ratio of 10 is equivalent to 20 decibels. And so now we can plug it in here. So we plug in 10 for there, and then we plug in our given 50,000 for a open loop and solve for beta. And we end up getting a beta of about 0.1, give or take. Excuse me. So we know that from the previous page here, beta 1 over beta is equal to this. Beta is equal to Ri over Rf plus Ri. So it's a ratio, basically. So we'll copy that back over here. So we just solved for beta as being 0.1. So we can use the formula relating beta to the feedback resistors that we just derived, and then solve for the ratio of Rf to Ri and get 9. So Rf over Ri needs to be pretty much spot on 9 in order to achieve this particular beta, which will give us an ASP, or a closed loop gain, of 20 decibels given our 50,000 open loop gain voltage ratio. So there's a bazillion combinations, obviously, that would give us that. But if we're going to say working in the 10,000 to 100,000 range, you can pick some appropriate standard ones or use a series combination depending on what you have. That's what that ratio has to be. Okay. Now, up in this expression, when we were deriving our beta in terms of these feedback resistors, we've kind of played fast and loose with this input impedance and defining the potential of point B with respect to ground, both straight through the resistors and over through the op amp. Well, that was kind of dicey. Exactly how did we use this Z in here? So now we're going to get a little stricter about that, and we're going to actually use a circuit model for the op amp. So we're going to slice open the op amp, and we're going to use one of those models that we looked at back in chapter 2 as a representation and zoom in on that a little bit more. And we're going to use that to actually get an expression for our input impedance under conditions of open loop and negative feedback closed loop conditions. So this is now starting into impedance effects for the series parallel feedback configuration, and we're going to start with input. So here's the inside of the op amp. We have our signal coming in, probably an AC signal. That's going to create a certain amount of input current, which we're going to later learn is negligible, but it's going to flow through some kind of resistor, or series of impedance generating circuit elements, mostly resistors. And as a result of that, we can define a Z input, an impedance input, in the open loop condition. And that comes down here to this point, and if we were in an open loop condition, this would be at ground. But we're not in open loop, so that current's going to flow through this Z in open loop, and we're going to have a voltage drop versus the input voltage up here. And we're going to end up with V feedback, because the inverting terminal out here is at the feedback voltage because of our resistor network. If we look inside the op amp going out, we go from ground within the op amp. We have a voltage source, variable voltage source, and we have a very small usually output resistor, and now we're at Vout here, ready to go into our load. And then here's our feedback network. So we can do some algebra and relate some of these together using Ohm's law. So rather than having our Z input open loop, which would be at this point, we're going to account for the fact that we have a feedback network and say we're going to define our closed loop input impedances in terms of this point right here. So our impedance looking from here to ground in the op amp, all the way to ground. Oh, but there's another way to get to ground too. We got two grounds, one here and one here. So if I'm standing here and I'm looking into this op amp representation of circuits, I can get to ground this way, or I can get to ground this way, because there's a ground inside the op amp. So I have parallel configuration to ground. But regardless, I can always define the potential and the resistance or impedance of this point with Ohm's law, because from the standpoint of this point, I've got a certain amount of current flowing. How much? Don't know, but there's some current flowing, just a little bit. So I can define my input voltage, which I have a source that just gave it to me, as whatever this input impedance is times whatever voltage is flowing. So Zn closed loop is equal to Vn over In. We can go further through the op amp and say, well, okay, current is flowing through this resistor. We have In that has to flow through this resistor from the non-inverting terminal to the inverting terminal. Well, this inverting terminal is at V feedback. And we know that the voltage difference between the non-inverting terminal and V feedback at the inverting terminal is called V error. We defined that earlier. So we can use that in this same expression. So V error is going to be the voltage drop over this resistor. We have In coming in that we defined up here. It has nowhere else to go. It flows over Zn open loop, and as a result gives us a voltage of that happens to be equal to V feedback over here. So we can say that the voltage drop over the open loop impedance is going to give us V error. Vn minus V feedback is V error. And that's coming just from this one application of Ohm's law. Okay, so we can say that the input current is a function of the signal coming in, Vn, and V feedback, if we have a feedback network that's connected to the op amp. Okay, well, In and Vn, if we relate those together, we get this. So we may be able to do some algebra, and using this circuit model we can give ourselves an expression for VNSP. So we're going to do that. We're just going to plug ourselves right back in. And again, we're going to do a little bit of algebraic wrangling to make sure that our final expression for VNSP only includes things that we could look up on a spec sheet or design in the circuit ourselves, like our two resistors here. So we start again with our ZNSP is our input voltage signal. That's the one coming into the circuit from like the thermocouple or whatever, divided by the input current. This is current here, which is probably going to be really small. So we can define that input current from, again, we can write it in terms of this equation, which we just observed from our circuit model. So instead of saying In, we're going to say V error divided by the open loop input impedance, that resistor. So we just stick right there in the denominator. But as we're doing that, we could say, now wait a minute. I remember a relationship between V error and the output voltage that we defined earlier. which is the output voltage over the open loop gain. So that was what we defined right at the beginning of the chapter. So we're going to substitute that in for V error, and that is in the denominator. And so we drop down here with some more algebra. So instead of V error over Z in open loop, we end up with V out over open loop gain, and with the Z in open loop in the denominator of this fraction, which is all in the denominator underneath V in. So we can simplify that a little bit, and we get V in times the open loop input impedance, that thing, times the open loop gain divided by V out. Okay? Oh, but wait a minute. V in over V out with the feedback network installed is just 1 over the closed loop gain. Oh, isn't that handy? Let's just throw that in instead of V in over V out. Because we can define that closed loop gain with, say, a beta or something else and not have to actually measure input and output voltages. So let's just substitute this in for these two terms here. So we do that, and we get an expression for the input impedance closed loop, our series parallel configuration, is equal to our open loop input impedance, something that's probably listed on a spec sheet, times the open loop gain, something else is probably listed on a spec sheet, divided by the closed loop gain. But remember, this has already been defined as the loop gain or sacrifice factor. So we can just write that to make it simpler. So to sum up, is that sacrifice factor again, our input impedance closed loop with negative feedback, in this case in the series parallel configuration, is equal to our open loop input impedance, something you can probably find on a spec sheet, times the sacrifice factor. And if you recall, the sacrifice factor is always going to be greater than 1, because with our negative feedback network, our open loop gain is always greater than our closed loop. So what we've done by bolting on that negative feedback network is we have increased our input impedance, which is great when we're trying to transfer a voltage signal. We're going to get less of a loss of that incoming voltage signal if we make this input impedance huge, because it'll faithfully replicate that signal through the op-amp and allow us to amplify it with very little loss or distortion. So this is another benefit that comes from using negative feedback. Okay, we're going to take a break here, and then we're going to take another look at impedance effects with negative feedback. We're going to look at output impedance, and I'm sure you all can guess that there will probably be some relationship to the sacrifice factor, and probably imagine that since we like low output impedance, we're going to hope that the sacrifice factor probably maybe ends up in the denominator, so we're reducing output impedance. And I'll give you a hint, that's exactly what it does. So I will end this recording now, and then we'll pick up again right at the same spot on my notes, page 10, and we'll go hopefully to the end and discuss output impedance, give a few examples, and then take a quick look at the parallel series configuration of a negative feedback network, which is great when we're concerned with current gain. See you then.